Hello, everyone, and welcome to our new series on tackling Kaggle's Playground Series competitions. I'm Karthik, and today we are diving into the current competition, Season 4, Episode 9 of the Playground series, Predicting Used Car Prices. It's a regression task where we have to predict a used car price given its input features. This challenge provides a great opportunity for data scientists of all levels to practice their regression model development skills and learn new techniques by solving the problem of predicting used car prices. Our task is to build a model that can predict the price of a used car based on various features. This is an interesting problem as it has applications in the automotive industry, finance, and even individual car buyers and sellers. As you can see, all of our submissions are evaluated on the root mean squared error metric. This is a common metric for regression problems, and we want to minimize this value to get the best possible model. Remember, lower the RMSE, better the model. If you want to know more about RMSE metric, let me know in the comments below and I'll make a video specifically about RMSE. Now let's take a look at the data page. The competition provides us with the following files. Train.csv. This is our training dataset. It also includes the target variable, which is price. And test.csv. This is the dataset on which we need to make predictions. And sample submission.csv. This is the file that shows the format in which we need to submit our predictions. As you can see from the dataset description, the data was generated from a model trained on a different dataset, the used car price dataset. It's a dataset which is collected from cars.com. It has 4009 data points. I will link this dataset in the description below. Coming back to our competition, data is generated so that it is a little bit cleaner than the real world data, and we will have more data points than just 4000. Let's take a closer look at the features we have. ID is the unique identifier for each car listing. Brand is the manufacturer of the car and the model of the car and the year in which the car was manufactured. It's under model underscore year. And mileage is the total distance the car has been driven. Fuel type is the type of fuel the car runs on. It could be gasoline, it could be electric, it could be flexi fuel. And the engine has horsepower, the liter capacity, and the type of engine like V6, V8. And transmission, this could be automatic, manual, etc. And the exterior color of the car and the interior color of the car. Now that we have a decent understanding of the competition and the type of data we are dealing with, let us start building our first model. Before we develop a model, first step for us is to get the data into our local environment. These are the CLI commands to do that. It downloads the data using Kaggle API. If you don't have Kaggle API, you can install using pip install Kaggle. Running these commands will get the data in the same structure as I did in my own repository. I have my data in a separate data folder. Now let us explore the dataset. We will be using pandas for data loading and manipulation throughout this series. We can see that we have 188,000 plus training sample data points and 125,000 plus test data points. This is plenty of data for us. So the first model and the first start that I got is, let's start with neural network because we are not data poor and we can train a neural network till convergence with this much amount of data that we have. Whenever we have a data set, it's always a good practice to separate your categorical variables and numerical variables. For this data set, except for mileage, all other features are categorical in nature. Some might confuse, hey, model year, that's a numerical value too. Why isn't it a numerical feature, but you have written it as a categorical feature? Because we don't want our model to learn any order or sequence in the years. It is more of a metadata information that the model would know about. Now that we have separated our categorical variables, basically everything except mileage, for our numerical feature mileage, we are applying standardization. By standardization, it means that we are scaling the values so all of them have a mean of 0 and a standard deviation of 1. This is a common pre-processing step that helps neural networks learn more effectively. Standardization is particularly beneficial because it ensures that all features contribute equally to the model's learning process, preventing features with larger scales from dominating the training. For example, just like mileage, if we have age of the car as one of the feature, it is not there in this data set, but let us assume it is there in some other data set. The scale in which the age values are roughly around 5 to maybe around maximum of 20 to 30 years, whereas mileage is in thousands of kilometers. It is much higher. Whenever we do that without running any standardization on numerical features, the model tends to overtrain on those models with higher scales, but that is not what we want because we want the model to actually learn which feature is more important. Now, coming to the data processing of our categorical features. First step we want with our categorical features is to convert them into numerical values so that the model can understand. To convert our categorical features into numbers, we are using the factorize method from the pandas library. This method is useful for obtaining a numerical representation of an array of categorical values. For further reference, I will leave this method's documentation in the description below. Once we have converted all of our categories into numerical values, next step is to remove rare category values. We are defining rare categories as those which do not even have 40 data points in the dataset. This is a common technique to remove noise in the data and also to prevent overfitting on outlier data. By outlier data, I mean rare data points which do not occur as frequently as the other ones. We are filtering them out based on now we have a frequencies, and after that at the end for each categorical feature we will have the number of unique categories present in that feature. Along with there is a plus one which is added for the rare category. Now that we have the numbers of 1, 2, 3, 4, 5, 6, these are not just important because we a better representation of the categorical features for a neural network would be in the form of a vector. A common heuristic to determine the embedding size is to take the square root of the number of categories. As of now, I could not find a reference for why this heuristic is a standard practice. If you are aware of it, please comment it down below. As soon as I find a reference, I will update the video description along with the link. I have taken this heuristic from a neural network starter notebook on Kaggle discussion forum. I will also leave a link to this notebook in the description below. Overall, for categorical features, we are converting them into numbers, then filtering out all the rare categories, and we are calculating the appropriate embedding sizes for each categorical feature. Finally, let's build our neural network model. Now let's look at the model architecture. We are using a neural network with separate inputs for categorical features and numerical features. For each of the categorical features, we have a separate embedding layer. This allows the model to learn different weight matrices for each category in the embedding space. In the end, we combine all of the embeddings and pass it to the dense layers later. Here I have three dense layers, each with 256 units and a ReLU activation function. All of these are just standard choices while building a neural network. We can experiment with several different hyperparameters. Finally, at the end of the dense network, we have a single output layer. At the end of the output, we will have the price of the used car based on all of the inputs that we have given to the model. Now to the training process. We are using five-fold cross-validation to ensure our model generalizes well. This means we'll train the model 5 times on different subsets of data and average the results. We do that using the k-fold object which is present in the TensorFlow library. And for reproducibility, we are using a random state. Coming to the training loop, the k-fold splits the data into train and validation. We'll have 5 different pairs of train and validation indices. For each fold, we will go through and train the model on the data split. For training the model, the optimizer we are using is Adam, and the loss we are using is mean squared error. And the metric we want to keep track is the root mean squared error, RMSE for short. That is the metric on which our model is being evaluated even on Kaggle. Along with it, we are also using something called as a learning rate scheduler. For each of these folds, we are training the model for 3 epochs. That means 3 times trained on the entire dataset. The learning rate that we apply in the first epoch is 10 to the minus 3, and even in the second epoch, we maintain the learning rate to 10 to the minus 3. And for the final epoch, we'll set our learning rate to 10 to the minus 4. This procedure is called learning rate annealing. I will link a research paper below about learning rate annealing and how it improves the performance of training a model. We have mentioned several things like k-fold cross-validation, learning rate scheduling, embedding layers, Adam optimizer, MSE loss functions, etc. If you want to learn more about any of these topics, please let me know in the comments down below and I'll make a separate video about it. Finally, let us train the model and see how it performs. Each of the folds RMSE values are 68,000, another 68,700, then we have a 74,000 RMSE value fold, then we have a 76,000 RMSE fold, then there is 76,200 RMSE fold. As you can see, that the RMSEs learned on each fold are wildly different. And that's why it is always a good idea to average out all of our predictions. Let us also look at the visualizations of how the model is getting trained. As you can see, both the loss and the RMSE values are decreasing with each and every epoch. This is a good sign that our model is learning from the data. And remember that RMSE is just the square root of MSE loss. So it is a measure of average error our model is making. So lower the RMSE value, better the model. We have a representative metric of how well our model will work on the new submission dataset. So let us create the submission file. In the predictions folder, we'll have a final output of our submission. Now open your Kaggle and click on the submit predictions and attach your submission CSV file, which I've already did before. There we have it. With a very simple neural network model, we got a public score of 72,328. And now let's look at the leaderboard for our standings compared to others. As you can see, we are at rank 514. With just a very simple neural network model, we have reached the 514, whereas the best submission model is at 71,891 and our score is at 72,328. We are just 0.6% away from the top scorer. Our end goal with this series is to reach in the top 100 of the leaderboard, and today is a decent starting point. In the next video, let us work on improving the model performance further. For this, I would be researching through all the discussion forums. Thank you for watching, and I hope you found this helpful. If you did, please like and subscribe for more machine learning content. See you tomorrow in the next video.